measurements on the rocks and soils. And to a geologist, the clues are in the rocks if you want to get inside it. Curiosity is, think of it as the robotic chemist for Mars. So it can do everything that Opportunity is doing today and then some. So obviously it's a larger rover. This weighs 900 kilograms. So it's 5 times the mass of Opportunity. A bigger rover can carry a whole bunch more stuff with it. The payload on this is about 75 kilograms, where the payload on Opportunity, a scientific payload, is only about 5 kilograms, so much more instrumentation. The rover, even though it's bigger, doesn't go any faster. It moves about as fast as a tortoise on the surface. But because of its large size, it can traverse over much larger obstacles. Because typically we can traverse over rocks about the diameter of the wheel. So these are 50 centimeter, 20-inch diameter wheels. So it's a 6-wheel drive system. It's a rocker bogie, what we call the rocker bogie. Actually, I'll draw those together. Curiosity is nuclear powered. It has what's called a radioisotope thermoelectric generator, which is uses plutonium-238, which is the non-fissile plutonium, has an 86-year half-life, and you just rely on the natural radioactive decay to generate heat. And as Dean mentioned, thermocouples then convert that directly into electricity with about a 4% conversion efficiency. So it provides, this design provides about 100 watts of electricity nearly continuously on a 86-year half-life exponential decay. So a continuous source of energy. But additionally, we take the waste heat from this. We have a set of radiators that capture that and use it to keep the rover warm. Because on Mars, you see temperatures, minus 150 degrees Fahrenheit, minus 100 degrees C on the surface. So it gets pretty cold. So the rover sees stereoptically. It has depth perception, just the way we use our 2 eyes. We also have, these are the color science cameras that have video capability, and you'll notice that they have a different aperture opening because you have a left and a right eye, but they have a different focal lengths. It is called ChemCam, and it is a laser spectroscopic system. There is a laser that has fiber optics that looks through this telescope that'll shoot a laser pulse at a distant target, vaporizing it, and then the same optics looks at the emitted spectrum, does a spectral analysis on that to determine the elemental composition. So it's it's not a rover defense system. It's a remote sensing elemental mineralogical thing. So when the rover goes up to a rock wall or face, we'll have that remote analysis as well.
Is there a possibility that you could somehow brush away or whatever if you wanted to get at least a little bit subsurface?
Okay, we're getting to that.
Okay.
Okay, so these are sort of the remote sensing instruments up here. We have a set of environmental monitoring system. This is called REMS. These 2 sort of cigar-shaped masses. There are a series of weather instruments, so wind velocity, temperature, atmospheric pressure. There's a radiation monitor. This is called RAD, so it's a radiation detector, so it's assessing the radiation environment for possible human exploration. On the right side of the back of the rover, there's also a neutron-based instrument called DAN, which uses a neutron tube to shoot 14 MeV neutrons into the ground and look for the moderation of neutrons for the presence of hydrogen. I worked with some people from Schlumberger who were doing down well hole neutron spectroscopy and putting gamma ray detectors down there for identification. So as the rover drives, it'll kind of map out the hydrogen content of the near surface with that instrument. But then we have the robotic arm on the front, and this gets to the contact instrumentation. So this is a 2-meter boom. There's about 75 kilograms of mass out of the end of this thing, so you can imagine holding out a 2-meter broomstick with 75 kilograms on the end of it. So you can understand why these actuator joints are quite large. Although on Mars, the gravity is only about 3/8 of what it is on Earth. So, but still we need to test it here on the ground. So these are heavily designed actuators. But there's a whole constellation of equipment on the end of this device. One is called MOLLE, which is the Mars Hand Lens Imager. It's basically a digital microscope, has color filters on it. It has active LEDs for illumination as well as UV LEDs, so you can actually do fluorescence measurements with it. There's a thing called the alpha particle X-ray spectrometer. This is using a small curium source to shoot alpha particles into the subsurface. to induce X-ray emissions, and then by analyzing the X-rays, you can map out the elemental chemistry. So you can do pretty much everything from sodium up through zinc on the periodic table. But I think the important instrument is the drill, which is it's a coring drill. It can drill maybe down to 20 centimeters, and the important thing is that it can extract those core samples from depth. So, as you know, you can't judge a book by its cover. You can't judge a rock by its exterior. You want to get inside. Importantly, that's where not only you can have pristine material, but preserved material, because we know that the environment on the surface of Mars is very hostile. Not only is it very oxidizing, but because of the lack of much of an atmosphere, there's an intense radiation environment which pretty much breaks down anything, particularly organic experiments in the belly of the rover. And this is, I think, is the big, important part of this mission. One of them is an X-ray diffractometer. So it'll do X-ray diffraction on the samples. So this will allow you to do very detailed mineralogical examination of the samples that you extract. The other instrument over here is called SAM, which stands for Sample Analysis at Mars. And SAM is a quadrupole mass spectrometer. It's actually a GC mass spec, so it's a gas chromatographic at the front end, quadrupole mass spectrometer, and as well as a tunable diode laser spectroscopy system. And it has the ability to look at everything on the periodic table. It has a sensitivity out to about 400 Daltons, about 400 atomic mass units, which covers everything on the periodic table, as well as complex organic compounds. And that's the exciting thing. And it'll also do the isotopic measurements. So one of the things it can do is it can actually not only take soil samples, but atmospheric samples, and look at the isotopic composition. It can detect methane over Mars. That Mars at one time was a habitable environment. That sometime around 3.5 to 4 billion years ago, Mars had a thicker atmosphere. It had sustained liquid water on its surface, and it had sources of energy. We found ancient geothermal sources on Mars. So you had the environment that could have supported an ecosystem. Because here on Earth, whenever you find a hydrothermal system like the geysers of Yellowstone or deep ocean volcanic vents, they're thriving ecosystems. Because you have liquid water, which we know is essential for life as we know it. You have the energy source to drive that ecosystem. So we know those kinds of physical conditions existed on Mars. So now the question is, was there the chemistry present? Was there the organic chemistry, again, as life as we know it here on Earth, was that present on Mars? And so that's one of the objectives of Curiosity, to see if there's an inventory of organic material. Now, we know that complex organics exist from non-biological sources. Meteorites have been found to have amino acids. So we can't determine whether it's necessarily of biological origin, but the important thing, are there hydrocarbons on Mars? Maybe Chevron wants to be first mover on that exploration.
20 centimeters?
Pipelines are probably.
So where you would look for organics would be entombed in mineral classes that tend to preserve organics, and that's clay minerals are one example. We know there are clays on Mars. Opportunity, my rover, is about to explore some clay minerals. Now, we don't have the organic detection capability, but we can establish the geologic context of those clays. Where we're going on Mars is a crater called Gale Crater. It's about 150 kilometers in diameter. It was flooded at one time. It's been excavated by subsequent erosion. We see evidence of clay minerals in Gale Crater. It preserves an ancient stratigraphy. There's about 5 kilometers, 3 miles of stratigraphy, exposed sample capabilities on it. So those will be used very sparingly when they think they have a high value target to try to investigate.
What about shelf life on the reagents?
When the rover drives on the surface and leaves wheel tracks, it leaves this repetitive pattern every wheel rotation. And it turns out that is a scientifically very valuable thing, because it's like laying out a ruler. So when you take a set of pictures and you look back at your wheel tracks, it's like you have a ruler laid out. So they wanted to do a similar thing here. And, okay, just for people in this audience, the bolt holes are actually a Morse code that spells out JPL. We actually originally had a JPL logo on the wheels, but NASA told us we couldn't do that. Gina, I don't know how you're on time. An aeroshell and a parachute to slow us in the atmosphere of Mars. You've probably heard the 7 minutes of terror. The last couple of minutes of that, it's a propulsive descent. So the rover has what's called the sky crane. I call it a rover jetpack. It fits over the top of the rover. Here's the rover kind of stowed up underneath, and then it gets lowered down on a bridle as it approaches the surface. And then the rover will do a soft touchdown on the surface. The sky crane then flies away and crashes, and then, it's no longer needed at that point. The reason for this is, first of all, this rover was much too massive for the airbags you might be familiar with the previous system. You just can't use airbags on this. The second was we wanted a more precise landing. We wanted to get to the high-valued science. When Spirit and Opportunity landed, we had a landing ellipse that was over 100 kilometers long. So that's touching down anywhere in Los Angeles County. And we needed to be able to land within Pasadena to get to the high value science, because you may want to go to a target, but you might land too far away. The other thing, with a propulsive landing, you might be saying, well, why are you using a sky crane that touches down? Why don't you just fly it all the way to the surface? Well, you have this jetpack on the rover, you want to get rid of it. So the other is, you don't want your propulsive system to compromise the scientific integrity of your landing site. And so you have these thrusters that are firing propellants that are, hydrazine that's, breaking down and will just, completely, contaminate the chemistry of your landing site, as well as those, each one of those engines is 800 pounds. There are 800 pound, I think something of the order of thrusters. So there's a huge amount of thrust. It's just going to blow away, blast away everything in the surface. So having the sky crane up high, keeping the thrust plume away from the surface, dropping down the rover, and then having that sky crane fly away and crash. So you maintain
orbit insertion, a flyby. Anytime there's a large event, this room gets utilized, and it's this room and the room just off to the left of us. And if you can't quite get the angle to see into that room, you can check it out on the way out, or there's also a live feed of it up in the upper left-hand corner. So as you can see, there's nobody in there right now. But you can see the famous American flag on the very back of the wall there. That's where all those great shots come from of Malachi and all the people sitting at their consoles for the landings and big events like that. So the people that sit over there, what that allows them to do is be very close to the people in this room. And what makes that important is because these are the people that control what we call the Deep Space Network, or the DSN. So the Deep Space Network is our vital communication link between Earth and any of our spacecraft at our moon or beyond. So we do not track Earth orbiters with our Deep Space Network, but anything from our moon or beyond, we use this system of antennas. And back in the 1960s, NASA said, okay, we need the ability to talk to anything in space, anywhere, anytime. And you can imagine the timing of that. You can imagine what we were trying to talk to, any place, anywhere, anytime. The Apollo astronauts, right? So the moon is not always visible from one section of the sky. If you walk outside right now and you look up in the sky, we're not seeing the same chunk that people in the other hemisphere are seeing. So we needed to make sure that at all times when our Apollo astronauts were out there in space, we could have communication with them. And then deep space missions were kind of on the forefront at that time as well, so we knew that we were going to need this network anyway. And what they decided was each station of antennas, each dish antenna, has a pretty good vantage point because our spacecraft are incredibly far away, that it can cover literally about 120 degrees of the sky at a time. So that's a pretty good chunk.